Asymptotic notations. We have algorithm. We are going to analyze the algorithm efficiency in terms of time complexity and space complexity, and how we are going to represent uh, efficiency of algorithm, that is called asymptotic notations. We are using asymptotic notations to represent the algorithm efficiency in mathematical form is called asymptotic notations. It refers to the computing of running time of any operations in mathematical units of computation time. And here, how much time it takes to produce a result, that's called time complexity, that can be analyzed, that can be represented using asymptotic notations. Is a mathematical tool for analyzing the efficiency of algorithm and behavior of algorithm. Here, time complexity depends on the input size. If number of inputs n increases, what will be the change in execution time t of n? What will be the growth? Is f increases, t of n increases linearly, or if n increases, t of n increases quadratic or cubic or exponential or factorial growth. That is the notations of performance of algorithm or behavior of algorithm with respect to input size n, which helps in analyzing algorithms running time or space complexity independent of machine specific constant. So we can, during running time, we can record the time execution in a computer, or we can do mathematical notations. We can apply some calculations and formula and constraints, so we can find out the efficiency in terms of mathematical notations without execution in a real time. It's called asymptotic notations. There are three cases in asymptotic notations: best case, average case, and worst case. Best case, if algorithm takes minimum amount of time or algorithm performs minimum number of operations, is called best case. It takes minimum time. And this average case, it takes average time in between best and worst. What's the worst case? If algorithm takes maximum amount of execution time, maximum time required to produce the result. If the execution time is more, it's called worst case. And how we can, there are what are the notations available? Big O notations, big omega notations, big theta notations. So big D O for best case, big omega for average case, and big theta for worst case. So we'll see one by one with example and definitions. And best case, if algorithm takes minimum amount of time or it performs minimum number of operations, is called best case. Worst case, if algorithm takes maximum time for execution or to produce a result, is called worst case. And the average case is the case between the best and worst case, is called average case. And big O notations, it defines the upper bound of an algorithm. It defines the worst case, how much maximum amount of time algorithm take. There's a maximum time taken by the algorithm is represented in the form of big O notations, that is called upper bound. And if n increases, what is the maximum running time or maximum execution time? For example, if algorithm takes at most n cube time, or it performs n power 3 steps to complete to produce the result, the time complexity is called order of n power 3. There's a cubic. In the worst case scenario, the algorithm won't take time more than order of n cube. So it's a maximum time taken by the algorithm represented by big O notations. Mainly big O notation represents the worst case complexity of algorithm. So worst case means the algorithm won't take more than order of n power 3. And this is the graphical representation of big O notation. And G of n is order of growth for f of n. F of n is the execution time. That is T of n or f of n. Finding order of growth for f of n. That is G of n is growth on input size n. That is n square or n. That is asymptotically less than or equal to G of n. So see here f of n, the graph f of n value is less than growth, C into G of n. So in the x-axis, we have number of inputs n. Y-axis, we have time complexity or f of n or t of n. In this big one notations, f of n value is less than or equal to growth. So growth is more than f of n because it gives maximum time or worst case time complexity. And big O notations, that is the lower bounds, the best case, how much minimum amount of time it takes to produce the result for input size n. It defines a best case scenario. And if to measure the minimum running time or space of an algorithm, we are taking with respect to the input size n. If it increases, what will be the minimum amount of time taken by the algorithm? That is called big omega notation. If algorithm takes least n steps, okay, they will not perform less than n. That is the best case. This is a minimum best called best case complexity. This omega of n. The algorithm takes at least n steps to produce result without considering the input size n. That is called big omega notation. Here f of n is greater than c of n or g of n is less than f of n because it shows the best case. So growth value is less than f of n. And big theta notation, that it shows the average case in between best case and worst case. So we cannot say algorithm for such input, it always gives best, always gives worst. So there may be a change. There may be a value between best and worst case. That is called average case. To measure the average running time or space of an algorithm with respect to input size n, that is called big theta notation. It takes at least n steps to produce the result without considering the input size. Here we have two functions, growth g of n and g 1 of n. That is f of n is greater than c1 of g of n and which is less than c to g of n. Because it's average case, there are two conditions. And we will see the order of growth. What is the order of growth? If n increases, what will be the growth or increase in time, the change of time, increase in time of execution, t of n, that is called order of growth. There is a function name is, we have 8 predefined order of growth functions, that is constant, logarithmic, linear logarithmic and quadratic, cubic, exponential and factorial. And see here, the top one takes minimum time, the bottom one takes more time. If algorithm has n factorial, for example tower of Hanoi problem, for this tower of Hanoi problem, growth is 2 power n minus 1. There is order of growth is 2 power n. It takes more time compared to all other algorithms. So here the last one factorial, it takes more time than other algorithms. And here the bottom to top time, execution time is reduced. Bottom is more execution time, the top is less execution time. So constant, so order of 1. Whatever may be the size of input, it takes one, performs only one operations. That is order of 1. Logarithmic, log of n, which is less than linear log n. That is n log n. Multiplication of n into log n log n. So logarithmic, linear logarithmic, and quadratic, order of n square. When n increases, d of n increases in power, n square, n 2 power 2, 2 power 3, like this. And cubic, n power 3, n into n. If n increases, the order of growth increases in cubic manner, then exponential, then factorial. And this is order of growth table. For example, take the last one, last row, n is 64, number of input is 64. Here constant means order of 1 value, whatever may be the n value, it takes only one operations, and that is 1. Order of growth is 1, that is fixed. This constant, it won't change. This is rare case for some problems. And logarithmic, so log of 64 value is 6. If algorithm time complexity is log of n, it will take only 6. It performs only 6 operations. For example, if we are telling time in seconds, it takes 6 seconds. And linear, if n is 64, The time is also 64. That is a linear n. N log n. It's a multiplication of n into log n. That is 6 into 64. If algorithm time complexity is n log n, execution time is 384 seconds. Then go to quadratic, 64 power 2, that is 4069. When we go for cubic, that is 2,62,144. And think of exponential, the value is very, very higher. That algorithm that will can take week or 1 month or 3 or 6 months to solve some problems. So if algorithm with exponential complexity is not a efficient one, and we will see the growth. So x-axis we have the inputs and y-axis we have the time and space complexity. See the graph order of one, the fixed one. If n increases in the x-axis, there is no change in execution time. And take log of n. If n increases, there's a light change, order of log n. It won't take much time. And see order of n and order of log n, the difference between these two, order of n, it's a linear. It took more time compared to log n. And take log n log n, it's a multiplication of these two. If n increases, the growth of change, the order of growth of change is more. See order of n square, n cube, and n factorial. N factorial for small number of input, the algorithm takes maximum amount of time. That is order of n cube. By using this graph, we can understand the different notations for solving the problems. Examples, order of one, irrespective of the input size. Whatever may be the input size, it takes only one. That is number, it performs only one operation. And logarithmic time, it's like binary search. And linear search is order of n, linear time. If n increases, the order of growth increases in n. And n log n, so multiple logarithmic time. Say efficient sorting algorithm, EdSort and QuickSort. The problem solved using divide and conquer approach, that will take only order of n log n time complexity. And the order of n square, insertion sort, bubble sort. Some sorting algorithm applies the brute force approach. The same problem statement solution is implemented without any optimization or modifications. That for that problem, the order of growth is order of n square.